Hello everyone and welcome to the fourth lecture. Morad here. So let's come back to our story. So in the caves, on the rocks, there were some drawings, a combination of symbols. So for the moment, let's focus on symbols perception by the persons independently and without really a combination or a context added to them. Call them symbols, drawings, codes, tokens, entities, objects, units, whatever the name you chose, just stick to it mentally because at the end, those names do not have any meaning for the learning devices that I have presented in the previous lecture, as they deal only with numbers and numerical signals to represent properties and features. So any type of data input, text, image, audio, actions, whatever, could be mapped to symbols or symbols combination. I will use symbol at index as terminology in this mini series, but I don't have any preferences as it is a pizza versus burger choice. So for example, the cloud here is a list of properties of numerical signals at the index 6. Call it whatever you want. List of properties, list of numbers, vector of numbers at index 6, or use the the fancy words such as word vec, embeddings, dense encodings, whatever the name you choose. It is a list of numbers stored in a list in a vector and positioned at index as a number 6 here for the cloud. And also we can say that can we even break down these symbols into sub-symbols or sub-tokens. And this process is called tokenization. And it's the subject of another lecture or another series. But here, intuitively, we can easily agree that these symbols have some properties that help the persons in the societies to distinguish between them. Now, the question is how to extract and find these properties, features, or characteristics. And to answer this question, we have two schools, the old school and the new school. The old school states that we need to start searching or brute forcing the possible properties independently of the goal to achieve and figure out some universal properties. I call this approach fixed properties. And the new school states that given a goal, so give me a goal, and examples of combinations of symbols, which is the data. The assumption there are unique properties to present these symbols that will help achieve that goal. So we can learn these properties along the way while trying to achieve this given goal. And this new school is learnable properties. So we have either fixed properties or learnable properties. And another important concept is the transformation. So these symbols, when they are combined or put in a context, there is some transformation applied to them that doesn't affect the essence properties of it independently. So they add extra information to the symbol to help put it in a context or a combination of symbols. To have an idea about this transformation, let's consider a simple space-time transformation, which is the position, rotation, scaling, and time shifts, for example. But the transformation is not limited to just space-time transformation. It is really a high-dimensional transformation. And this transformation can be either fixed, or learnable by a learning device. And in the transformer architecture, they proposed learnable properties and use inputs as index and pass them in a learning device that will try to figure out the properties of each token or each symbol. And they use a fixed transformation and they call it positional encoding. So this is a really a special case of a fixed transformation. And my question here was, can we do a partial transformation update of this symbol? So assume, for example, that the symbol has some x, y, z, and time shifts plus other properties, and add either fixed or learnable transformation to patch just these parts here that is affected by the transformation, and also learn differently those properties. And also another question that's maybe interesting or not, just see that why not have dynamic property size, dynamic list. And also I have done some experiments on fixed properties and fixed transformations, and present, for example, one of my experiments. Each symbol or each token, each character of the sentence of the text is presented with a square signal with a fixed frequency. And I presented the position as a shift in time of that square signal. And the context, I mean, to have a sentence, what I have done is just adding the signals of the shifted, the signals of the shifted, frequencies. And training, I have done two approaches for training, either with the softmax to predict the frequency as class, or to predict the time square signal of a symbol. And in the inference, I have two strategies as well, either doing inference by class, which is a classification, or when you use the second approach, you use the frequency transform or Fourier transform of the predicted square signal to detect what is the maximum frequency speak out by the model. So my goal of this ongoing experiment was to use the fixed properties and fixed transformations to find a way to have dynamic and infinite context using decomposable signals such as Fourier transform, polynomial decomposition, Taylor series, or probabilistic decomposition to predict next token or symbol as a task. So I have used the old school to present the symbols as signals, and the new school to use the learning devices to have deeper representation of those signals. And I have shared these approaches in my GitHub repository. So in the Fourier positional embeddings, you will see that there is basic and simple that use one learning device and presentation of square signals of the text, characters of the text, and learning devices combined with the positional Fourier positional embeddings here, for example. I have trained this example with presentations. In this file, I have many presentations of persons, such as my name is Emily, etc. And what I have done here is I have described the process here. So I use two learning devices. I call them eyes, and one simple learning device that try to look for the attention, a very, very basic attention. And so each character of the context size of the sentence, which is 8 characters, is represented with a square signal with different frequency and a shifts in time to present the position, which is the transformation in general, of the character in the context text. So the model was trained with 99 presentations, and when I infer it with a softmax, I got coherent presentations that samples from the training set. So I have used the technique, to choose the max probabilities from the softmax, but when I use that, I generated really samples from the presentations, and it tries even to sometimes extrapolate, because my name is Anne, that is not present in the training set. So, but it's somehow find a way to say Anne and comma and continue with the same pattern of the presentation. And also here I have, my name is ABCDE, and I found it really interesting as a result just for the character based training. It's very simple way. It's just using the characters, but we can use tokens, subwords or words to train large ones and complicated models. But just for the illustration of using the fixed transformation and learning devices. So if you are interested in such resources, I have shared many projects that goes from simple experiments such as the Fourier and learnable devices to complete projects, a chatbot that uses LLM with function calling, and another way to approach RAG, which I called knock knock doc, how to chat with your documents. And I'm really happy that they have some stars and forks, and I really appreciate if you like them to share them with the community. And I have also other ideas, such as trying to find a way to mix the cryptocurrency world with the AI world, and exploiting the energy used for cryptocurrency mining to train new kind and architectures for large language models. So I will let you explore and maybe share. And with that said, thank you very much and see you in the next lecture.